The study focuses on the application of expected force, a newly proposed centrality measure, in identifying key nodes in network-based epidemic models. Expected force effectively predicts the spreading power of nodes and identifies key nodes and immunization targets. However, its high computational cost poses a challenge for its use in large networks. To overcome this limitation, two parallel scalable algorithms for computing expected force scores are proposed. The first algorithm is based on the original formulation, while the second one adopts a cluster-centric approach to improve efficiency and scalability. These implementations significantly reduce computation time, enabling the detection of key nodes at large scales. The importance of identifying key nodes in epidemic models is highlighted, as they can play a critical role in the epidemic process, such as super spreaders or individuals that bring the epidemic from one subpopulation to another. The proposed algorithms are designed to efficiently scale to large networks, exploiting modern parallel architectures. Performance analysis on synthetic and real-world networks demonstrates that the GPU implementation of the algorithm can efficiently scale to networks with up to 44 million edges, achieving speedups of up to 300 times and 50 times on average compared to the simple parallel solution. The concept of node centrality is crucial in understanding the spread of epidemics on networks. One such centrality metric is the expected force of infection, which ranks nodes based on their potential to spread the disease to nearby nodes. This metric is particularly useful in small world networks where long infection paths are rare, and the spreading power of a node mainly depends on its local network structure. The expected force of infection is defined as the number of different ways a node can lead to other nodes catching the disease once it is infected. To address the computational cost limitation, an efficient algorithm for computing the expected force of infection has been developed, along with scalable parallel implementations. This allows for the processing of large graphs and provides a comprehensive analysis of the performance and scalability of parallel expected force algorithms. A systematic analysis of individual spreading power in susceptible infected recovered epidemics on real-world and synthetic networks is also conducted, comparing the results with popular centrality metrics and demonstrating the expected force of infection to be the best predictor of empirical spreading power. In the realm of network-based epidemic models, a novel approach has been proposed to identify key nodes that significantly influence the spread of diseases. This method leverages the expected force of infection, EF, which measures the outdegree of clusters centered on a node, thereby providing insight into its potential as an epidemic spreader. The authors of this research paper also detailed their innovative parallel computing approach to efficiently calculate the EF. By employing cluster-centric processing, they are able to mitigate load imbalance issues and enhance computational efficiency. This methodology is then compared with other centrality metrics, focusing on their ability to predict epidemic outcomes based on node properties. The primary goal of this study is to demonstrate the efficacy of the EF in identifying critical epidemic spreaders. To achieve this, the authors analyze the correlation between the EF and various epidemic-related node properties. Through this analysis, they aim to establish the EF as a reliable metric for predicting the spread of diseases within complex networks. In essence, this research presents a groundbreaking approach to understanding and controlling the spread of epidemics. By utilizing the expected force of infection and advanced computational techniques, scientists can better identify and target key nodes in network-based models, ultimately leading to more effective strategies for disease prevention and control. The research paper discusses the role of centrality measures in understanding the spread of diseases within a population using the Susceptible Infected Recovered (SIR) model. The SIR model is calibrated on a common influenza-like illness, ILI, with an average time to recovery of 3 days and a reproduction number of 1.3. It's applied to a network where the average degree is denoted by less than k greater than. The paper focuses on 3 measurable features: empirical spreading power, the ability of a node to seed a global epidemic, and the effect of immunizing nodes with an expected force, EF, value. Empirical spreading power of order D is defined as the average number of nodes in the infection subtree rooted in V of depth D. The likelihood of a global epidemic is estimated as a function of the centrality of the index case. Centrality measures, such as degree centrality, betweenist centrality, and PageRank, are used to quantify node importance based on topological properties. These measures can capture localized or global network structures and are essential in various fields including social network analysis, biology, and urban design. In the evaluation of various centrality measures to identify key nodes in network-based epidemic models, the authors focus on degree centrality, betweenist centrality, PageRank, and expected force. Degree centrality, defined as the number of edges connected to a node, indicates a node's potential to directly infect more nodes in a spreading process. Betweenist centrality measures the frequency of a node's appearance in shortest paths between other nodes, making nodes with high betweenist centrality scores more central to the graph. PageRank scores nodes based on their connections to important nodes, with the damping factor influencing the score. This metric models a random walker traversing the network, with high-scoring nodes more likely to be visited and infected during an outbreak. The expected force metric aims to capture the force of infection a node exerts on the network by analyzing possible sets of nodes infected by that node. It is based on the concept of transmission clusters, which represent possible infection states after a certain number of transmission events. The out degree of a cluster quantifies its ability to further propagate the infection. The formal definition of expected force relies on a parameter J, usually set to 2, and involves calculating the normalized cluster degree for each cluster rooted at a node. The expected force of a node is then defined as the entropy of the distribution of normalized cluster degrees. The equation for expected force is provided, where EF, V, is the entropy of the distribution of normalized cluster degrees of CV, with CV being the set of clusters rooted at node V, and DC being the normalized cluster degree of cluster C. The research paper discusses the parallel computation of expected force in a graph, focusing on the efficient computation of cluster degrees. It proposes an algorithm working in 3 phases. First, collecting pairs of neighbors for each node. Second, computing the degree of each cluster by summing node degrees and adjusting for triangles. And third, computing the entropy of cluster size distributions to obtain the expected force of infection. The algorithm's efficiency is demonstrated through a lemma showing its work and critical path are both O, n delta squared max, where n is the number of vertices and delta max is the maximum degree. This approach addresses previous workload balancing issues and inefficiencies in the original formulation. The novel parallel algorithm for computing the expected force in network-based epidemic models operates in 3 phases: cluster generation, histogram updates, and computation of the expected force. It starts with an empty set of clusters and iterates through all nodes in the graph, generating clusters based on their adjacency lists. In the second phase, the histograms of node degrees within each cluster are updated, considering the number of clusters with specific degrees and adjusting for overlapping clusters. Finally, the expected force for each node is computed using the entropy of its histogram. This parallel algorithm's computational complexity is O, n delta squared max, significantly better than the vertex-centric approach's O, n delta squared max complexity. The efficiency improvement stems from the algorithm's ability to visit each cluster only once, avoiding redundant computations. The implementation of this new parallel cluster-centric algorithm is discussed, including a comparison to the vertex-centric approach. The vertex-centric approach is not suitable for GPU implementation due to workload imbalance and was implemented using OpenMP for multi-core CPUs, with a fine-tuned scheduling policy for optimal thread utilization. In the context of parallel computing and load balancing, this section discusses the implementation of a cluster-centric algorithm for the efficient fragmentation (EF) method on a GPU. The algorithm utilizes dynamic scheduling to assign tasks to threads as they become available, allowing for flexible and efficient load balancing. This approach is particularly suited for GPU implementation due to its ability to handle irregular workloads and small iteration spaces. The cluster-centric algorithm is designed to leverage the massive number of threads and high-speed memory access of GPUs. It uses an edge-centric approach to generate potential clusters by reading the entire edge list stored in coordinate format, COO. The algorithm performs a 2-step visiting of the graph, resulting in a balanced workload for each vertex. Vertices are then divided into chunks to generate clusters, which are checked for triangle formation and have their degree updated accordingly. This process is performed using CUDA streams to maximize GPU utilization and overlap computation with data movement. The paper also presents an experimental analysis of the EF method on both synthetic and real networks. The synthetic network used is obtained through the Urban Social Network (USN) model, which considers factors such as age, geographic distance, and sociability in generating an unweighted undirected spatial network. Real contact, social, interaction networks of varying sizes and features are also included in the study, all of which are publicly available. The scaling of expected force in network-based epidemic models is a crucial aspect in identifying key nodes efficiently. This involves an experimental setup utilizing DGX2 with NVIDIA A100 GPUs and an AMD EPYC 7742 64-core processor. The performance analysis highlights the vertex-centric and cluster-centric implementations of the expected force algorithm, showcasing strong scaling results and efficiency metrics. Notably, the limitations and future work discussed in the paper are also significant areas of consideration. The authors delve into the scalability and efficiency of the vertex-centric algorithm, implemented in OpenMP, and the cluster-centric algorithm, implemented in CUDA, for graph clustering. Figure 2 illustrates the strong scaling of the vertex-centric algorithm on RMAT_16/8, demonstrating that the OpenMP-based runtime grows much faster than linearly with an increasing average degree of the graph. This highlights the scalability issues of the vertex-centric approach. Furthermore, the authors analyze the time spent computing each cluster in Figure 4, revealing that the OpenMP version becomes less efficient as the number of processed clusters grows, resulting in poor performance on larger graphs. This is attributed to the fact that the number of clusters grows much faster than the degree of the graph, as shown in the last column of Table 1. In contrast, the CUDA implementation of the EF algorithm, depicted in Figures 3 and 4, exhibits better scaling properties, with a slower growth rate of running time despite the increase in total work. The cluster processing rate remains almost constant, indicating an optimized design. Figure 5 compares the computation time of all implementations, including the existing sequential version, on various graphs listed in Table 1. Due to limited resources, computations exceeding a 24-hour time limit are excluded from the plot. The results demonstrate substantial advancements of the parallel implementations of EF over the sequential implementation, with the cluster-centric implementation using CUDA outperforming others. The research on scaling expected force. Efficient identification of key nodes in network-based epidemic models is centered around optimizing the computational efficiency of expected force (EF) calculations in network analysis. A cluster-centric algorithm implemented in CUDA significantly outperforms a vertex-centric OpenMP implementation in terms of speed, showing a maximum speedup of up to 300 times and an average speedup of 50 times compared to the OpenMP version. This enhanced efficiency enables the calculation of EF for large-scale graphs, such as a contact network with 1.6 million nodes and 44 million edges, in under 4 minutes. Furthermore, the authors explore the empirical relationship between centrality metrics and node properties during an epidemic simulation, emphasizing the importance of the expected force in identifying key nodes. In the realm of large-scale graph analysis, the expected force, EF, centrality measure plays a crucial role in identifying influential nodes and predicting information or disease spread. This study presents a comparative analysis of two algorithms for computing EF centrality: a cluster-centric approach implemented in CUDA and a vertex-centric implementation using OpenMP. The comparison is conducted on synthetic RMAT graphs with varying average degrees and a fixed size of approximately 216 vertices. The results demonstrate that the cluster-centric CUDA implementation outperforms the vertex-centric OpenMP implementation in terms of clusters per millisecond, particularly when the average degree increases. This suggests that the cluster-centric approach may be more efficient for graphs with higher connectivity. Furthermore, the authors compare the running time of 3 different EF implementations on real-world graphs of varying sizes, as detailed in Table 1. The results, shown in Figure 5, indicate that the EF metric demonstrates equal or better performance than other centrality measures in identifying vertices responsible for multiple infection chains, with the exception of the social_location graph. This study contributes to the understanding of efficient algorithms for computing centrality measures in large-scale graphs, which is crucial for various applications in network science. The findings highlight the potential benefits of using cluster-centric approaches, especially in graphs with high connectivity, and underscore the importance of further research into optimizing algorithms for such tasks. In network-based epidemic models, understanding the relationship between expected force, EF, and global outbreaks is crucial. Research has shown that EF is strongly correlated with various centrality metrics, including degree, betweenness, closeness, and eigenvector centrality, indicating its ability to identify key nodes in a network. To further investigate this relationship, simulations were conducted using the SIR model, where a vertex with a specific EF value was designated as the index case of an epidemic outbreak. The results reveal that the likelihood of a global outbreak increases with the EF of the index case, confirming previous findings on smaller graphs. The study also examines the impact of immunization on epidemic spread. Simulations were run where 5% of the network was immunized, with varying average EF values of the immunized vertices. The results show that immunizing nodes with high EF values significantly reduces the likelihood of a major epidemic in most networks. Furthermore, the time course of epidemics and its relation to the EF value of the index case were analyzed. Observations indicate that, except for the high school network, both the epidemic length and the time to reach the epidemic peak decrease as EF increases. These findings suggest that individuals with high EF values are more likely to trigger outbreaks, spreading the disease faster among their acquaintances, and giving rise to shorter but more severe epidemics. In terms of methodology, the study proposes an efficient parallel algorithm for computing EF, addressing limitations in scalability and efficiency. The cluster-centric parallel algorithm exhibits better time complexity and scalability, with a significant performance improvement of 300 times compared to the original algorithm when implemented on an NVIDIA GPU. The authors propose a computational solution to evaluate the expected force, EF, score, a centrality measure that correlates with the spreading power of nodes in a network. This solution enables the computation of the EF score on large-scale graphs, as demonstrated by an experiment on a 44 million edges graph, which was completed in just a few minutes. The results of experiments on networks of varying scales demonstrate the applicability of the proposed solution in real-world contexts. Figures 7 and 8 illustrate the proportion of global outbreaks and epidemic size for epidemics starting from vertices with different expected forces of infection, with and without 5% immunized individuals, respectively. These results show that the EF score is predictive of the ability of nodes to start an epidemic and to hinder it when preemptively immunized. The authors emphasize the significance of centrality measures, particularly in the context of the COVID-19 pandemic, and suggest that there is a need to move towards dynamic or temporal graphs and hypergraphs. They compare the results of extensive SIR simulations with centrality values, demonstrating that the EF score correlates better with spreading power than other popular centrality metrics, such as betweenness centrality, on various real-world and synthetic networks. The proposed solution offers a scalable and efficient way to compute the EF score, making it a valuable tool for understanding the spread of epidemics and informing strategies for controlling outbreaks. The current study scales expected force in network-based epidemic models to efficiently identify key nodes, emphasizing the importance of considering complex graph structures. Building upon previous works, such as those by Sunitra Gupta, Roy M. Anderson, and Robert M. May, the authors reference Mark E. J. Newman's work on network-based epidemic spread. The summary of Fig. 9 illustrates the mean value of the time to peak, epidemic length versus expected force, averaged over 100 global outbreaks, providing a comprehensive understanding of network behavior under different spreading conditions. This foundation serves as a starting point for exploring the expected force on these graph structures, paving the way for future research. The authors present a comprehensive review of existing literature on betweenness centrality, graph processing, and epidemic modeling. They cite various studies on parallel algorithms and efficient multi-threaded implementations for evaluating between centrality on massive datasets. Additionally, they reference works on approximating between centrality through sampling and edge-centric graph processing using streaming partitions. The authors also discuss graph processing on GPUs and provide an overview of network epidemic models with two levels of mixing. They cite studies on measurability of the epidemic reproduction number in data-driven contact networks and centrality measures in social networks. Furthermore, they review graph theory applications in biological networks, network security and contagion, and hubs in the human brain. They also reference works on statistical mechanics of complex networks and influential spreaders in complex networks. The authors conclude by citing studies on asynchronous distributed memory triangle counting in LCC with RMA caching, as well as effective vaccination strategies for realistic social networks. They mention OpenMP, an industry-standard API for shared memory programming, and reference works on inferring urban social networks from publicly available data and creating maximum entropy data-driven spatial social networks. In the context of network-based epidemic models, identifying key nodes is crucial for understanding the spread of infectious diseases. Efficient methods for scaling expected force are essential, as social contacts and mixing patterns play a pivotal role in disease transmission. Research has employed various approaches, such as Socrates, which utilizes social contact data sharing to evaluate COVID-19 mitigation strategies. Another notable method is RMAT, a recursive model for graph mining that aids in identifying influential nodes. The Network X library has emerged as a valuable tool for exploring network structure, dynamics, and function, thereby facilitating a deeper comprehension of epidemic spread. A vital aspect of this research is the exploitation of multi-level parallelism, enabling the efficient exploration of large-scale graphs. This approach is critical for unraveling the complexities of disease transmission and identifying key nodes that drive the spread of epidemics. By developing scalable methods for identifying influential nodes, researchers can inform targeted interventions and more effectively mitigate the spread of infectious diseases. The integration of social contact data, graph mining techniques, and parallel computing has the potential to revolutionize our understanding of epidemic dynamics, ultimately leading to improved public health outcomes.